Welcome to Topology Sessions. Last class we have discussed some of the motivation for topologies. This topology is previously called as rubber sheet topology due to the fact that extension or compression of a material cannot affect its topological properties. Today we will discuss about the definition about topology and some of the examples. Topological spaces. Topological spaces. Definition: a topological space is a pair we will denote that as x comma script t, where x is a set and script t, some may be name this as tau also, no problem, whatever the notation you are following. But in your textbook, everything in this version given as script capital letters of English alphabets. So I am pronouncing this as T. And T is a family of subsets of X satisfying three conditions. First condition is empty set belongs to script T and X belongs to script T. That is the entire set. Second condition, script T is closed under arbitrary union. And third condition, script T is closed under finite intersection. So this is the idea of topological spaces. Now the family script T is said to be a topology. It's said to be a topology on a set X. And members of tau, script T, members of script T are said to be open in X or open subsets of X. So this is the definition of topology. You will be very thorough with this definition, then only we can move further. So topological space definition is a topological space is a pair x comma t where x is a set and t is a family of subsets of x which is satisfying three conditions. First condition is empty set and the entire set belongs to this family. And second one, this family is closed under arbitrary union. And third one, this family is closed under finite intersection. So a empty set and entire set belongs to this family. Then this family is closed under arbitrary union and this family is closed under finite intersection. Don't confuse with 2 and 3. It is arbitrary union. This is finite intersection. Now the family T is said to be a topology on a set X and the members of T are said to be open in X or open subsets of X. Exactly, topology means you have studied in your first sem class real analysis. Now in this paper we will study the generalization of all the concepts that you studied in your real analysis classes. With the real analysis class you have studied about open sets. So here the open sets are said to be in that real analysis class you have studied open sets in terms of metric. Okay, uh, dx comma y less than epsilon for every y or something like that, and you will say that that's going to be an open set. Or in the real line you will take all the open intervals and you will say that these are going to be the open set, or it should be the union of two open sets or something. But here in topology, open set means whatever be in the members of your family of that you considered for defining a topology, that members are said to be open sets. We can have an example here. Example, let x is equal to set A, B, C. And suppose I am taking my tau as phi x and singleton, sorry, not singleton. If I am taking BC, okay, will it be a topology? Let us see. I'm taking empty set. So first condition is satisfied. Empty set and this entire set belongs to the set, right? Next, what I want to have is closed under arbitrary union. So arbitrary union, since we have considered only a finite set, arbitrary union will reduce this as finite union only. Okay. So we take two elements from here and take its union and check whether it belongs to this set or not. Okay. When you're having union with an empty set, you will get the same set. When you're having union with X, you will get X itself, right? So when you're having now you want to check for intersection. So empty set with intersection this, empty set, this with intersection this, you will get again this set. So this will form a topology, right? So you can have another topology also. If you are taking this as T1, T2 can be empty set and entire set should be the. Now if you're taking singleton set A, will it be a topology? Or you can have this two, BC, again I'm taking. So these all will form topologies. There are so many topologies you can define on this three element set. I have mentioned only two. Only thing is that you want to check whether this three condition is holding or not. That is empty set and entire set will be there in this collection. And if there is a member here, then if you're taking the arbitrary union, it will be there in the set. And if you're taking finite intersection, it will be there. So we will have lots of other examples too. After defining or after having two definitions. We will come across lots of examples. Definition: a sequence, a sequence Xn in a topological space, in a topological space X tau is set to converge, is set to converge to a point, y of x if for every open set, for every open set u containing y, there exists a positive integer, there exists a positive integer n such that for every integer, n greater than or equal to capital N, xn belongs to u. A sequence Xn in a topological space Xt is said to converge to a point y of x if for every open set U containing y there exists a positive integer n such that for every integer n greater than or equal to n, Xn belongs to U. That means you may be familiar with the convergence idea in your real analysis class. So here I have got a sequence of points which converges to a point x. Now your real analysis class, your idea is that if this xn converges to x, then for any neighborhood of x containing, if there is an epsilon neighborhood of x, may have lots of points from this, right? That is, xn is said to be converged to x if for every epsilon greater than 0 there exists a n such that d of xnx is less than epsilon for every n greater or equal to capital N. This was the idea you have studied in a real analysis class. But here, what you are saying is you take an open set containing x. So what is open set over here? Open set means if you are having a topology here, take an element of that topology. Nothing else. No need of taking epsilon. No need of taking this metric and all. You take an open set means you take an element from your topology. Now, if that topology element belongs containing the element x, then what it says, there exists a positive integer n such that for every integer n greater than or equal to n, xn belongs to u. So if this is the case, u is open set containing, here you are taking y, okay, instead of x you are taking y, then there exists a natural number n such that xn belongs to this open set for every n greater or equal to capital N. So this is the idea in topological space how a sequence converges. Next definition is a topological space A topological space is said to be metrizable. Metrizable if its topology can be obtained from a suitable matrix from a suitable matrix on the underlying set. On the underlying set. So what is follows is when a topology is said to be metrizable, you got a space X with a topology here, right? Collection of subsets of X. Some topology script T will be there. Now it is said to be metrizable if you are using a metric for defining the elements of top. Okay, if you are taking this real number R and you are defining your script to as set of all x minus epsilon comma x plus epsilon. So what's the meaning of this? Meaning is that d of x y collection of all y such that d of xy is less than epsilon, right? So you will have these open sets. So you're making use of the idea of metric here. So we will say that such topologies are going to be metrizable. Next we are passing to examples of topological spaces. Examples of topological spaces. First one is in discrete topology. We are denoting it as X capital T. So in discrete topology means, suppose we are having a set X equal to some 1, 2. Now I am having script T I am defining as empty set and this entire set. Only these two elements. Now this will form a topology, right? First condition is satisfied, phi and x are there. Now this is closed in the arbitrary union. When you're taking union, you will get only x. Now it is closed in the finite intersection too. Finite intersection, if you're taking empty set with x, you will get empty intersection, and intersecting x with x, you will get x itself. So this will form a topology. This topology is said to be indiscrete topology. So tau is containing only two elements. One is empty set and the one is the entire set. In this set, in this topology, we can note that in this topology, every sequence converges to every point. Every sequence will converge to every point. See, you have taken this to be as x. So let your x is equal to 1, 2. Okay, and your topology is t is equal to empty set and x. And we take the sequence 2, 2, 2, extra, right? Then we take the sequence 1, 2, 1, 2, extra. And you take one more sequence, 1, 1, 1, extra. So these all are the sequences can be defined on over this set. In the real analysis, you have studied this 2, 2, 2 constant sequence will converges to 2 only. But in this case, this sequence may converges to 1 also. Seems to be strange, but this will converges to 1 or 2. You can see how. Sequence definition, go for the convergence of sequence definition. What we have to do? You have to consider an open set which containing your limit, right? So suppose I'm taking this to be S1. Now you take an open set which containing 1. Open set, as I mentioned, here open means the members of this topology. Now this topology, you consider an open set containing 1. Empty set and X are the only open sets here. So an open set containing 1 means it is nothing but your entire X. Now any open set containing this 1 will contain all these elements, right? So this sequence may converges to 1. Similarly, you can take for 2 also. You take an open set which containing 2. So when you're having an open set which containing 2 means from here you can go for the elements of this topology which containing 2. That is only X. Now we want to say that after a particular stage all the members of this sequence belongs to this X. That is also true. So this sequence may converges to 1 or 2. In the same way, this sequence. In general case, we will say that this sequence does not converges. But this sequence also converges to 1 or 2. And here, as we discussed the sequence 2, 2, 2, 1, 1, 1 also may converges to 2 or 1. See, I have taken only 2 element set. If you are having some 5 element set means you can have 5 limit for one sequence. So this is the idea. We are saying that in this topology, every sequence converges to every point. Next example is discrete topology. First one was indiscrete topology. In indiscrete topology, we are having only 2 elements in a topology, that is empty set and the entire set. Now here, discrete topology. Discrete topology is also called power set topology. Power set topology. So from this idea, it is clear what should be the members of the topology. The members of this topology are all the subsets. So we are having X tau with tau is equal to, sorry, not tau, T is equal to collection of all subsets of X. So take all the subsets of X, it is going to be the discrete topology. For example, you take the set 1, 2, 3. Now, here the tau is collection of all subsets. First it should be empty set and X should be there, right? For a topology. Next you consider all the subsets, that is still considering all the singleton subsets. 1, 2, 3. Next we can go for 2 element sets, right? So 1, 2, 1, 3, 2, 3. Any more is the 1, 2, 3, 4, 5, 6, 7, 8. Only 8 subsets should be there. Since the elements are 3, you have got 2 raised to 3 subsets. right? So 2 cube is 8. So this is the discrete topology. Okay. Now you may studied about discrete metric. Okay. Now this topology is induced by discrete metric. This, sorry, not metric, topology. This topology is induced by discrete metric. And remembering what is discrete metric? Discrete metric is defined as d of xy is equal to 1 if x equal to y and 0 otherwise. Sorry, x not equal to y, right? So x not equal to y, it is 1, and if x equal to y, it is 0. Now the only convergence sequences, not the only convergence sequences in a discrete space, in a discrete space are those which are eventually constant. Eventually constant means after a particular stage it should be constant sequence. That is called eventually constant. So when you're having a sequence like this, uh, 1 2 1 2 1 2 1 2, then all the members are 2 means it is said to be an eventually constant sequence, because after a particular stage you are getting everything as constant here. So this is an eventually constant sequence. So what will happen to this sequence? Will it converges to 2? Let us see. If this is the sequence I am taking in this topology, will it converges to 2? So you should consider the open set which containing, here only 1 and 2 are there. So first you consider the open set which containing 1. So the open set which containing 1 are singleton 1 is the 1 2 is the 1 3 is the there x is there. So this much of open sets will contain 1. Now check whether all these open sets may contain the terms of the sequence after a particular stage. It is not possible since we are taking singleton 1. 2 does not contain in singleton 1, right, after a particular stage. So this sequence cannot converge to 1. Now if you're taking 2 means you're having the open set which containing 2. So go for the open sets which containing 2. So what are they? The open set which containing 2. One is 2, another one is 1 2, right? And next is 2 3, and next is x. These are the open sets which containing 2. Now if you're having, you check whether after a particular stage will these open sets contains all the terms of the sequence. It's true, right? Because everything containing 2. So this will converges to 2. So this sequence converges to. Thus, in a discrete topology, the convergence sequences are eventually constant sequences. Next example is cofinite topology. Third example, cofinite topology. Cofinite topology. Let X be a set, X be a set, a subset A of X is said to be is said to be cofinite cofinite if its complement if its complement X minus A is finite. So X be a set, a subset A of X is said to be cofinite if its complement X minus A is finite. So whenever a set's complement is finite, we will say that that set is cofinite. Right? Tau consists of all cofinite subsets, all cofinite subsets of X and the empty set. That is, tau consists of all cofinite subsets of X and the empty set. Why I am taking this as empty set? Because whenever your empty set is cofinite if and only if X itself is finite. Okay, so note that the empty set is cofinite if and only if X is or X itself is finite. X itself is finite. Then this tau is a topology on X. Tau is a topology on X. So you want to prove the question for you. You want to prove this tau is a cofinite topology. So what and all you want to prove? Tau consists of all cofinite subsets of X. That means uh, complement of that set is finite. Now you want to prove both empty set and entire set. Entire set definitely belongs to this because X minus X you will get empty set. Empty set is finite, right? So X belongs to tau. Now to take uh, arbitrary union of subsets of this cofinite subset and make sure that that belongs to tau, and you take finite intersection and make sure that that belongs to tau. Now what will happen if this set is going to be a finite one? So note, if X is finite, X is finite, it coincides. It coincides means the cofinite topology. The cofinite topology with the discrete topology. With the discrete topology. Or we can say that if X is finite, it coincides with the discrete topology. Let us take your X as finite one. Okay, so take an example, X as ABC. Okay, now we want to find the cofinite topology. The cofinite topology. So how to find the cofinite topology? You take a subset of X, and if its complement is finite, means that set belongs to T, right? Now subsets of X. What are the subsets of X? First one is empty set. Another one is X. Another one is singleton A. Another one singleton. I'm taking a singleton B and singleton C. Next one is two element sets I should consider. So AB, AC, BC. Right? These are the subsets. Now we take the complement of this. 5. 5's complement is X. Will X be finite? Yes, given that X is finite. So your top containing the element 5 or the empty set. So empty set belongs to this set. Next you take X. Now take the complement of X in X. Complement of X in X is empty set. Whether empty set is finite? Yes. If empty set is finite means its complement. That is X belongs to the topology. Now we take singleton set A. So I'm taking singleton set A, its complement X minus A I should consider. So X minus A is BC, right? Now this is finite. So that belongs to our topological space as BC. Next I should consider B, and I should consider X minus B and check whether X minus B is finite or not. Evidently here X minus B is finite, and that will result as A comma C. So that belongs to my topology. Next I should consider C, its complement. Its complement is AB. That is also finite. So that also belongs to this collection. So this I have covered. Next is AB. If I am taking AB, its complement in X is nothing but singleton set C, and that is finite. If that is finite means I should include that in my topology. So C is not. Next AC, its complement is B, that is again finite, so I should include here. Next element is BC, its complement is A, that is also finite, so I am incorporating that also here. Now any more subsets I have missed? No. So I am getting this to be as the entire subsets of A, right? So this is coinciding with my power set topology or the discrete topology. So whenever a set is going to be a finite one, this will coincide with a discrete topology. Thus, for finite topology coincides with a discrete topology whenever X is finite. Okay. So we have discussed about the definition of topology. Yeah. Definition of topology, then topological space, then some examples, and definition of sequence convergence. Again, metriceable definition, Now, a few more examples of topological spaces. One is indiscrete topology. Next was discrete topology and confinite topology. And next class, we will discuss some more examples regarding topological spaces. So I'm concluding here. Thank you for your patient listening. Thank you.